In this section, section 2.5, we will be discussing way up here at the top function transformations. But before we can get into discussing anything about function transformations, we first need to know which four parent functions will we be dealing with. And so here they are in all their glory. We have four different ones over here. On the top left, we have the quadratic parent function. We're going to get really in depth with those very shortly in this course. Over here, we have a cubic parent function, and you'll notice that with this cubic parent function, just like a quadratic has a square, and that's what separates them from linear functions. And when we were talking about equations, the square separates them from the rational equations and the square root equations. When you're talking about a cubic function, this exponent 3 is what separates it. We like to see that exponent 3, and that's how we know it's a cubic function. A square root function, that's pretty self-explanatory. What makes a square root function just by looking at the equation here. And then the absolute value function, we put the absolute value bars around the x. So you may have noticed that over here in these different colors, we have these tables. And these tables are the parent tables for these parent functions. And it is important to know these points. So if you look over here in the quadratic parent function, I'm going to start in the middle of this table right here at 0, 0. That point is right here. And then I'm just going to move down. So 1, 1 is this point right here, and 2, 4 is this point right here. And if I put these other 2 points above the 0, 0, that means we will have the point negative 1, 1 and the point negative 2, 4. These are very important points to know for the quadratic function when we begin to graph that. Over here for the cubic function, we have 5 more points to know, and we have 0, 0, 1, 1, negative 1, negative 1, and on this graph here, I don't have enough room to put these other 2 points, 2, 8, and negative 2, negative 8, so I'll just estimate something like this. That is negative 2, negative 8. And then way up here, somehow, something like this, that will be 2, 8. So it is important to know these points as well, even though I don't have the room to put them on this graph. And again, those points will be important to know when we begin to graph. Down here for the square root function, we have 0, 0, 1, 1, and 4, 2. So those are the only 3 points that you will need to know for the square root function. And then lastly, with the absolute value function over here in the bottom right, we've got 0, 0, 1, 1, 2, 2, and then negative 1, negative 1, negative 2, negative 2. For some reason, the scaling changed in this last graph. So these are the 5 points we'll know for the absolute value function. And you might wonder, well, holy smokes, how am I supposed to remember all these tables when I'm trying to figure out which function I'm supposed to be using and the names of those functions? And there's a very easy way. You want to remember all of these numbers, negative 2, negative 1, 0, 1, 2. It's the same for the quadratic, cubic, and the absolute value function. So how do you come up with all these numbers, these f of x numbers? Well, you just substitute these numbers in for x. So negative 2 down here, negative 2 squared is positive 4. Negative 1 squared is positive 1, right? We have our inputs and our outputs. When we substitute in a 0 in for x, we get back a 0. When you substitute a 2 in for x, you get back a 4. So it's all the inputs and outputs. So quadratic means squared, so you'll just square all of these numbers to get these. Cubic means third power, so you will cube all of these numbers to get these. Absolute value, you turn any number that you put in here into a positive number. So negative 2 becomes positive 2, negative 1 becomes positive 1. 0 stays 0. 1 is already positive here. It stays positive 1. 2 is positive. 2 stays positive. All of these numbers are 0 or positive. So that just leaves the square root. And with the square root, you want to remember your first three perfect square numbers, 0, 1, and 4, and you just take the square root of those to get these values. All right, so now that we have some basic idea of what these parent functions are, we want to look at transformations. So how I have this table set up is here we have the functions to this side of the table, and we have the transformations down this side of the table. And so there's a lot going on here. So if you want to have, or if you're given a cubic parent function and you're told to shift it vertically, that is either shift it up or shift it down, then you're going to have an equation that looks something like this. So this table explains a lot of things, and we're going to go over a lot of what all of these mean in the next page. So all of that table is daunting to see it all at once. So here I'm going to break it down, and this is a lot of reading and a lot of explaining, but it will break everything down that you need to know. So the first type of translation that we are going to look at is this horizontal translation. That is, if you take a look at one of those graphs on the first page, one of those 4 basic parent functions, and you're told to move it left or right, that's a horizontal movement. What that means is that, and if you go back and look at the table, all of those horizontal movements use h. And h will eventually be replaced with a number, depending upon how far left or right you're moving the graph. But you'll notice that h is being subtracted directly from the x variable inside grouping symbols. So that h is paired up with x, either by parentheses, a square root symbol, or absolute value bars. So when you have something paired up with x, that means it affects the x variable. And if you think about that, the x-axis is the horizontal axis that moves things left and right. When you say the x-coordinate is 4, you know you are moving to the right. So when that happens, the h affects the x variable and will shift the graph left if h is positive. So we've got this thing. Shift graph left if h is positive, and it will shift a graph right if h is negative. And at this point, you might be thinking to yourself, whenever we move to the right, like here, shift a graph right, all of those x values, when we start moving right, are positive. But this h you're saying is negative. Okay, and if we move left, just like if you're starting at an origin and I say the x coordinate is -4, you're going to move to the left. But if we're moving left, that means the h is positive. What's going on? That sounds like it doesn't make a whole lot of sense. Well, one thing I want you to keep track of, one thing I want you to remember, is this phrase right here. X's are crazy because they do the opposite. Not only does that work for almost every single horizontal translation you will ever do in your mathematics career, but it's also a good life lesson. I'll leave that there. Moving on. Vertical translations. If you go back and look at that table, the vertical translations, there's a number k being added in each of those functions. But you'll notice, like the h up here in this first part was inside grouping symbols. It was in parentheses with x. All of the k values are just being thrown out back. They're not grouped up with x, which means the only other variable it could be affecting is the y variable. And if you think about the y-axis, it is the vertical axis. So the k value shifts things vertically. And so it will shift a graph up if the k is positive, and it will shift the graph down if k is negative. And that makes sense. And it really makes sense because we're not dealing with x's anymore. So y variables act exactly like they're supposed to. X variables go a little crazy and do the opposite. And then we have these two reflections, and we can get a little more in depth into that a little later. But we can reflect over the y-axis if there is a negative inside the grouping symbols directly in front of the x variable. That's how you will get a reflection over the y-axis. And then lastly, the reflection over the x-axis, which is much more common if there's a negative being multiplied outside of grouping symbols, but it'll still be in the front of everything. That's how you know that it'll have a reflection over the y-axis. I'm sorry, x-axis. So, in these next 6 examples, I have some, I think I want to do examples 1, 3, and 5 to give you a chance to try to do examples 2, 4, and 6 on your own. So all we want to do right now is look at what is given to us. So in example 1, it says you have this as the parent function. It'll be good to note that that is the quadratic parent function, x squared. So the question becomes, how do you transform the parent to get the new function, this? And that should be a question mark. All of these should have question marks. So how do you transform the parent function to get this? I'm looking for words. In words, how does that minus 3 affect the graph, and how does that plus 2 affect the graph? Well, I'm going to underline this minus 3 in red, and I'm going to underline this plus 2 in blue, just so we can talk about it. It looks like since we have something either added or subtracted here inside with x, inside grouping symbols, that's going to be a horizontal translation. And since this is a negative number, x minus 3, we will have a translation 3 units right. Because remember, x's are crazy. You think because this is negative that it's going to go left, but x's are crazy, they do the opposite. They're going to the right. Now this number outside, this plus 2, is not in grouping symbols with x. It's just kind of thrown out back, maybe neglected if you want to think of it like that. This will be a translation of 2 units up. And that is because this is a positive 2. Any numbers out here act just like they should. So this positive 2, it's not in with the x, so it's affecting the y variable, right? G of x and f of x are the same thing as y. And it is acting completely normal. So it is moving up 2 units. So we come down here and we have x cubed. This is a cubic parent function. And so how do you transform the parent function, this thing, to get this new equation, this new function? Well, I'm going to underline the number that we have here. That's plus 1. So that will be a translation left 1 unit. So you may have noticed that I worded this one a little bit differently than this one, and that is totally fine. You're allowed to say this one way or the other, as long as you're giving me translation, how many units, and which direction. So translation left 1 unit. Perfect. And again, remember, since this is in parentheses with x, this is doing the opposite. So you think it's positive, hey, it's going to go right. Nope, it's in there with x. It's going to do the opposite, it is going left. Now in this last example, we have three things to describe. The first one is kind of just hanging out here in front. So there's a negative. Here we have a +3, and out back there's a +2. And we've already talked about that before. We already know that that is a translation up 2 units. We talked about that up here in example 1. Also, we have this +3. That is a translation. What do you say? Left 3 units. And that is because this 3 is positive and it's inside a set of absolute values. It's paired up with x in there, so it's going to do the opposite. And then this negative in front of everything. If you go back and look in your notes, that is in front of everything. This is a reflection over the x-axis. And so I'm going to pause for a few seconds to give you a chance to pause the video so you can try examples 2, 4, and 6. So for these last 3 examples over here on the right, there are, in this first one, this is a square root parent function. It's pretty easy to tell by the square root around the x. In the transformed function over here, this -4 is outside of the square root. It's just chilling out back. So that means that this is a vertical movement, and since it's negative, that will be a translation down 4 units. Over here in example 4, again with the square root parent function. So maybe this will make more sense that this -4 was outside of the square root, just like this +3 is outside of the square root. So that acts normally, it's a vertical movement, translation up 3 units. This -2 is inside of the square root with x. So instead of it being left, remember negative means right 2 units. And then the negative in front means a reflection over the x-axis. And then there's something very similar down here for the last example. So now we will do these examples in the exact opposite order. So in these next 4 examples, I'm only going to do 2 of them for you so you can practice a couple of them on your own. So we'll look at example 1. Given the fact that we have this parent function, which ends up being quadratic. I'm not going to write them this time, but it's important to know which one you're dealing with. What is the new function, g of x, if f of x is translated left 4 units and reflected over the x-axis? So translated left or right, that means that this number should be paired up with x, maybe in parentheses, maybe. Well, I guess since we have a quadratic, it's going to be a set of parentheses. So left 4 units, you're going to want to write a -4, but this will actually be an x plus 4. That's what will tell you left 4 units. And so since we have a quadratic parent function, you want to make sure that that entire set of parentheses gets squared. And something similar is going to happen over here when you get in the cubic territory. Hopefully I'm not giving too much away for that. But also, we have this information. This is reflected over the x-axis. So what that does is it tells you to put a negative in front of the entire thing. And so now we can just say that this equals g of x, the new function. Right? So we were finding a new function, g of x. So that's it. This is your answer. The example 3, right underneath it, we have this function, this parent function, f of x equals the square root of x. Clearly the square root parent function. So the question becomes, what is the equation of the new function g of x if f of x is reflected over the y-axis and translated down 1 unit? All right, so down 1 unit, that is a vertical movement, so I know that's going to be hanging outside of the radical. So that's going to be there. And let's see, I know that the reflection over the y-axis means there will be a negative directly in front of the x. So this negative, let me do this, reflected over the y-axis in purple, this negative will be hanging out directly in front of the x. Directly, not outside in front of everything, but directly in front of the x. So now we just have to go back and remember which parent function are we dealing with, and that is the square root parent function. So I need to make sure that the negative is in front of the x inside of the square root, and that the minus 1, since it's a vertical movement, is hanging outside of the square root. So g of x equals that. I'm going to pause for a few seconds to give you enough time to pause your video for you to try example 2 and 4. So here are the answers for the last two examples, example 2 and example 4. Not 100% complete. I wanted to make sure that you understand that this is the cubic parent function, and because of that exponent 3, this set of parentheses will also get an exponent 3. That's what sets a cubic apart from everything else. And the last example down here, example 4, this is an absolute value parent function. And since the 3 has to be paired up with x in some sort of grouping symbols, we're going to put the absolute value symbols around the x plus 3. So these are your final answers for example 2 and example 4. And this is the final answer for example 3. So moving on, the graphs. So you can see that when we have horizontal translations, it is quite literally just taking this center graph, right? Even with the points that we mentioned earlier, negative 1, 1, to negative 2, comma 4, 0, 0, positive 1, positive 1, and positive 2, positive 4. You can see that if you have x minus 2 squared, that quite literally takes all of the points and just shifts them over to the right. And similarly, you can see here that x plus 3 squared takes all of the points and shifts them over 3 to the left. So whenever you see an x value or a constant being added or subtracted in parentheses with the x value, you can just shift the graph left or right. In example 2, you can see the square root function. And here it is 0, 0, 1, 1, 4, 2. Those are the 3 points I told you to remember for that. You've got this plus 2 in this green example, this plus 2 hanging out here. So it just takes the graph and shifts all of the points 2 units up. Here they are, that point, and that point. Or over here in this x square root of x minus 3, it takes all of the points and shifts them down 3 units. So you can see this is the same, they have the exact same shape. A reflection over the x-axis. In example 3 here, you can see that we are dealing with the absolute value of x. And if the negative goes in front of everything, it is not in front of the x, it is in front of the absolute values. That the original graph in black here gets reflected over the x-axis. And similarly, you can see that this graph with the square root function, notice that negative is on the inside, and that's why the graph goes essentially from pointing to the left, pointing to the right to pointing to the left. It gets reflected over the y-axis. So let's try graphing some of these translated functions. The first thing you're going to want to do is identify what is the parent function. So I know this is a quadratic parent function. We'll do examples 1, 2, and 3 really quickly. This is a cubic parent function, and this clearly is a square root parent function. We will talk about the domains and ranges after we graph these. So what I want to do, how I want to graph this, or graph these functions, is first doing number 1. With the quadratic parent function, do you remember those points I asked you to remember? We had 0, 0, 1, 1, and 2, 4. And then negative 1, 1, and negative 2, positive 4. So what I want you to do to start graphing these is to remember that table and put x's where the parent function would be. So then it looks like I want to know how are these x's going to move. Well, I know by the minus 2 in here that those are going to go right 2 units, and that this plus 4 out here, I know the points will then move up 4 units. So each one of these x's is going to go right 2 and then up 4. So that'll go right 2 up 4. So let me draw in some x's in blue to show what that means. So this far left x will go right 2 up 4. So I'm going to put a dot there now because that is the last transformation for that point. So this point, this next point, x, will go right 2 up 1, 2, 3, 4, right there. This point will go right 2 up 4, right there. This x will go right 2 up 4, right there. And I covered up the x that was right here. But that x will also go right 2 and up 4. So I have 5 blue dots now that look like this. And so that graph got moved right 2 and up 4. So now we can talk about the domain and range of this thing now that we have the graph. It looks like because this graph goes left forever via this arrow and right forever via this arrow, that the domain here will be negative infinity to infinity. And the range, again, starts at the bottom, the lowest part of the graph, the transformed graph. So it looks like the lowest y value here is 4, and it will go off to forever up to positive infinity. So 4 to positive infinity. All right, moving on to the cubic function. We get to talk about our first reflection over the x-axis. So with the reflection over the x-axis, that is what you're going to want to do first before moving anything left or right. So what I want to do, again, with some red x's are put the points on here. So I've got that point 0, 0, 1, 1, and 2, 8, all the way up there. And negative 1, and negative 2, negative 8. Those were those values in the cubic parent function table. So reflecting everything over the x-axis means this point way down here will go way up here. So I'm going to put a purple dot or purple x up here. This x will get reflected over the x-axis to there. That one is on the x-axis, it does not change. That x will go there, and the very last x will end up down here. So the purple x's represent the reflection over x. Now we can come back up here and move right 3. It looks like we're going to go right 3 and down 1. So each purple x, you're going to move it right 3 and down 1. I'm going to do that in blue. So from here, I'm going to count 1, 2, 3, down 1. And this next x here, I'm going to count right 1, 2, 3, down 1. And this x, next x, 1, 2, 3 to the right and down 1. This x, 1, 2, 3, and down 1. This x, 1, 2, 3, and down 1. So you always want to plot your parent function points, do any reflections second, and then shift left, right, up, or down last. So the blue graph here would be your answer. We do not need these arrows. I just wanted those arrows there so you could see where everything was going. There we go. So the blue graph is your answer. For the square root function, remember that the x's are at 0, 0, 1, 1, and 4, 2. And then it looks like we're going to move these left 1 and up 4. So the translations you can do all at once. So I'm going to start with this first dot, at the first x at 0, 0. I'm going to go left 1 and up 1, 2, 3, 4. And I'm going to put a dot. So I'm going to move this x left 1, 1, 2, 3, 4. And this last x, I'm going to move left 1, up 1, 2, 3, 4. And there it is. Oh, and I didn't talk about the domain and range. All right, so the domain and range of the cubic function, and this is great because it works like this with the cubic function all the time, is negative infinity to infinity and negative infinity to infinity. Don't think about it for the cubic functions, just write it. The domain for a square root function, you may notice, it's as far left as we can start, the x value, which in this case is negative 1. And it goes forever to the right, so it's going to be negative 1 to infinity. The range is the lowest y value, so you'll notice, remember if you use the horizontal line here, that the lowest y value is 4, and then it goes forever up after that to infinity. So this is negative 4 to infinity. I am going to give you an opportunity to try the rest of these examples on this page all by yourself. So there's example 5, that is an absolute value. There's example, it's out of order. That's example 11, that is another absolute value. And then you have 3 more examples, 7, 8, and 9. And I will give you a few seconds of silence to pause your video to give these a shot.